Kailash, is the recording on?
Yeah, Rishabh, we can start.
Thank you. Hello, everyone. Welcome back to another session with us on our guided course in AZ-204, which is a Microsoft certification on Azure solution, developing solutions in Microsoft Azure. And I'm Rishav Chatterjee, a developer in 365 technology. I'll be conducting this session. This session is about developing solutions on Azure Cosmos DB, which is a Microsoft service on NoSQL data. Last session, we covered unstructured data on Azure Blob Storage, and concerning that, we now the next session will be on Azure Cosmos DB. We'll be starting on the session, and in the end of it, we'll be conducting a QA. Uh, that's so. This is a like revisiting the course structure that we are following. So today we are on Azure Cosmos DB, and the next session will be on implementing infrastructure as a service solutions. So stay tuned for more uh, sessions of this exam path. So starting on developing solutions, what is Azure Cosmos DB? So Azure Cosmos DB is a database which uh, earlier it was called uh, doc, document DB, and it was revamped to Cosmos DB. It is a planet scale NoSQL database. So it is a service provided by Microsoft. And in this session, the objective is to learn how we can use that in our applications and how to connect it with our .NET or any other uh, language applications like Python, Java, but we'll be focusing on .NET in this session. And we'll be using .NET SDK v3, which is version 3. That is a SDK made like particularly for querying Cosmos DB queries and stuff. We'll be also learning what the consistency levels which we will be getting in Cosmos DB and how we can set it according to our requirements as per in our application. And also we'll be learning what the partition keys are, how we are going to partition, what partition types we get, and what we can do, and like how to create a partition in our database. So moving forward, we have three modules to cover, sub-modules to say. The first is going to be exploring Cosmos DB, the fundamentals of it, how the hierarchy works, what resource types we get, how the uh, resource units are, like how we get built and uh, those things. The second part will be implementing partitioning, how the partition works. And the third one will be going through a working code demo, which in .NET, which will be using to create a container, a container, and items inside Azure Cosmos a database. We'll be inserting and deleting like simple CRUD operations using our application. So uh, before knowing any new technology, we might want to ask what are the benefits of it. So what are the benefits of Azure Cosmos DB? Why we should be using it apart from the structural SQL database that we already have? So the main reason between these two is the scalability and the consistency levels that we get in Azure Cosmos DB. In SQL, the data structures is already predefined, which is not the case in Cosmos DB. Cosmos DB is fully NoSQL database, and the scalability feature is unlimited, and we get infinite throughput also. And the main benefit of it is planet scale. as we go to NoSQL database option, we get the we can reap the benefits of a fully distributed database where we have multiple data centers across the world and data can be replicated across it. Like we can have a data center in US and a data center in India. So a user who is residing in India doesn't have to wait for the data to become fetched from US to access the application. They can directly use the data from Indian servers or Indian database. So, and the same goes for across the world. If we have a application and it scales massively in like worldwide, goes worldwide in a few months or days even, like it can we can scale it through Cosmos DB. It takes care of the scale or horizontal scaling where each uh, we can allocate resource around the users that we get. We can see where the users are coming from and allocate if there are any Azure data centers available in that space. So that is a very useful feature, and we can do it just by click of a button. Like we can just go to the map and select which region we want to deploy, and it will do all the work for us, like replicating all the data and deploying the database there. Moving on, we have multi API support. So as Azure Cosmos DB is a NoSQL database, but we have support for 5 different APIs, starting from NoSQL to MongoDB to Gremlin uh, to Cassandra, which and table APIs. So why do we need those APIs? So that we can seamlessly structure already like previously built application using those APIs. Like we don't have to re-engineer our app, re-engineer our data models and stuff. We can run SQL queries seamlessly using this SQL API in our Cosmos DB. Sorry. And same goes for MongoDB and other APIs. So we have multi API support for Cosmos DB. And next comes elastic scalability. So what it means is we can allocate throughput as per the need arises. Like we can dynamically the resource will be allocated, or we can also set it like to a threshold. We will be getting to that later. So what happens is, let's say like a horde of you like users get the peak user time is around 6 p.m. IST. So we don't have to wait and scale the database as we'll be anticipating the users will be increasing in 6 p.m. The database will be doing that for us and it will do that in milliseconds. And the changes will be taken care for us. And the another huge benefit is consistency level. So very few NoSQL database gives us a consistency spectrum as Cosmos DB provides us with. By consistency, we mean with distributed database comes a trade-off of throughput and consistency. Like, do we want to have a strong consistency or eventual consistency? We'll be covering that in great detail in later slides. But the main thing is we have to select a trade-off. Like, what do we want? Because as there are many different database across the globe, let's say a user writes in a database which is in US, and to sync that data, there is a minimum latency time that gets created for the data to be synced across all the database that is there in the world. So let's say I am in India and I am trying to read the data, but it is already updated in the US database. Because the data is not synced yet, I get the stale data which is in the server, like in the database in India. So the database consistency property is not valid here. So in SQL, the simple SQL database, it always tries to uh, implement or check the acid properties, which is good. But sometimes where when we don't need the acid properties, we can't, in those scenarios we can't get away with it in SQL. And here we get a spectrum of consistency as per our requirements. Here we get 5 different consistency level, which we'll be going through uh, in later slides. So we can choose from them as per our requirement. So these were the few benefits of Azure Cosmos DB and why we might want to learn about it more. This is the resource hierarchy structure of a file system in Azure Cosmos DB account. So in the top, we have a database account which we'll be creating. And while creating the database account, we have to specify which API we'll be using. I will be going through that as I give a live demonstration while creating an account. And inside that account, we have databases. And inside databases, we have containers. And inside containers, we have different documents with each document having its unique ID. So there can be multiple database and each database has to be unique, of course, because its namespace has to be identified inside the database account. And in a azure uh, azure account, we can have maximum up to 50 database accounts, and that is also a soft limit, because if we try to contact them, they will of course increase the number of database accounts that can be present. So for us normal users, we can have maximum up to 50 database accounts in a uh, Azure account. So inside database accounts, we have databases, and these database has containers. And these containers, depending on the Cosmos API, container is realized as collection, table, and graph or other stuff. And we can also view it as different type of entity items that we know from SQL. Like it can be, or MongoDB, it can be called a document as of NoSQL terminology, or a row, or a node as per graph, node or a edge. So these are depending on how we model our data. We can call them whatever we want. But in Azure Cosmos DB, as it is a non-structural database and it stores documents, it will be stored as a document, and it doesn't restricts with the structure of the document as in SQL. Like in SQL, we have to give the set the structure before as we design, and then we insert a document inside the data. But in SQL, every item inside the container can have a different type of structure. Like let's say I have a ID and name in item number one, and in item number two, I can have ID, name, and other parameters like class, standard, roll number, two. And inside, and they can be nested too. So that is what we mean by a document. It's a like a JSON document. Moving on to the next slide. This is a container which we saw here. So this is a so containers are how we provision the throughput and storage. When we create a container, we give them how much how much throughput we want and what storage that will be required. The throughput is nothing but the rate at which the uh, data will be read or moved between the reader and the query who's making the query, or who's like how where it is getting stored. And we also define the partitions in while we create a container. So partition, there are two types of partition. Going over it briefly, one is logical partition and one is a physical partition. So that which kind of partition we want to choose will be set while we create a container inside the database. And we also have a option to configure the throughput, how we want to use it. Like we have two options of dedicated versus shared. What it means is there are many containers in a database. So by dedicated throughput, we mean that each container has its own throughput and it will that container will only use that throughput. No other container will be using it. But in shared throughput, is what we mean is that inside a database, if a container is not using its all of its resource throughput, by which I mean, and another container wants that is in need of that resource and it doesn't have it already, then they can share the throughput that is as allocated to them between themselves. So that option we have to configure when we create a container. And this is the same thing that we saw before, like we can call a item inside a container in SQL terms, an item in Cassandra terms, a row in MongoDB or a NoSQL database term, we can call it a document. In Gremlin API, which is used to query graph type of data, which is used in like social networks and other applications like that, where we have to map different kind of data. There are many relations between them. We call them node or edge, and in table at API we call it item, as similar to SQL API. These are just the nomenclature that is used as per the end user terms, what API they will be using. Then coming on to consistency levels. It is very liberal, I would say, in the consistency levels. Like it believes that consistency is a spectrum other than giving it binary values like strong or eventual. We have a whole lot of types between them, like starting on with strong, we have bounded staleness, we have session consistency, we have consistent prefix, and we have eventual consistency. As we move from strong to eventual, our consistency gets weaker and the throughput gets higher. But the consistency also gets weaker. So in strong consistency, it means that the data is same in all the instances of the database. In all the replicas of the database, we will always get the same value no matter where that user is querying that data. And in eventual consistency, there is no such promise made to us. Like if the sync is not yet happened, the data will get there is no order in which we will be reading the data, and there is also no promise made that we will be getting the same data as what was written in another database somewhere else. So delving deeper into this consistency levels one at a time, we'll be moving first to what we have is strong consistency. So here is a graph where this is a primary database and these are all secondary read databases. So we also have a concept of read database and read write database and a write read database. So what read database is that the data which will be written, edited or inserted will always be done in a read write database. And when we want to only read a data, it will be done by a read write database or a read database. So data when it is written will be done in read write database, and when it is read will be done in both those databases. So in strong consistency, let's say in 9 a.m. a value was written, like we have a value at equal to a, and it in all those other secondary databases we have the same value in this time, which is a. And let's say in primary database at 10 a.m. we change the value from a to b. So uh, then it will get synced to all the secondary databases, and while it is syncing, let's say C2, which is client 2, tries to read at 10:10. It has not yet synced. how we know that it has not yet synced? Because the primary database hasn't got an acknowledgement from these two that yes, I got that data. So before ACK is received by primary database, if any client tries to read any data from any database, it will get the stale data only and not the updated data. As we can see in 1010, client 2 tries to read from server 2 or secondary 2 database, it gets the value A. And in 1020, it tries to read, client 1 tries to read from secondary 1, and it also gets the value A. And as we get an acknowledgement, we get the value A at 1040 A. This time and the difference in time is taken just for example. It is not hard and fast, like it takes milliseconds, but just for the example, we have taken it this much longer, like 40 minutes to just sync between three databases. So as we can see, strong consistency offers a linearizably guarantee. Like it guarantees to serving request, and the data is same in all the instances of the database. A client never sees an uncommitted or partial write. Users are always guaranteed to read the latest committed write, even if we have to wait for the data to be synced across. So that was strong consistency. And then moving on to bounded staleness. In bounded staleness, we have an option to set the variable of time, that is how much time it will take to sync the latest data. Here it is taken as 2 hours, but I think it's like 10 seconds or something like this in uh, Azure, as per uh, Azure. So here we have a staleness variable which is set to 2 hours. And here we can see the primary, secondary, and the client is there in the scenario. So let's say at 10 a.m. value is A, and uh, it's the same in secondary also. So in 12 a.m. value A is updated to B in primary database, and it is updated to secondary then and there. So user client tries to read data from secondary or primary, both the database will give the same data if uh, before because it is being tried to be read at 12:30, which is not 2 hours after it is updated. It still gets the stale data, even though the value has been updated at 12 p.m., which is set to B. So after 2, like 12, 1, and 2, the value will get updated, and all the users will get the updated data when they try to query it. So it also guarantees that every user has the same consistent uh, consistent data across the database. But we have a we have a like we can set the consistency time as per our need. Like we know in this many hours it will get updated, so we can sync at that level our application also. The reads might lag behind writes at most k versions of an item or by t time interval, whichever is reached first. In other words, when you choose bounded staleness, the staleness can be configured. So that is the main difference between hard consistency, strong consistency, and bounded staleness. That the staleness can be configured. It was not the case in strong consistency. It can be configured in two ways. Here it is already only shown that the time is set, but we can also set it to the number of versions that needs to be updated before the data is synced, and also the time interval t, which is shown in the example. that it will take 2 hours for them to sync the data across the different replicas of the database. Moving on to another consistency, the next one, we have session consistency. Session consistency is the most used consistency across all this consistency that we went till now, as we will see why it is the case. Sessions consistency within a single client session reads are guaranteed to honor the consistent prefix. Monotonic reads, monotonic writes, read your writes and write follow reads guarantees. This assumes a single writer session or sharing the session token for multiple writers. What we get with session consistency is that the order of the data is same. Like order of the data will be getting the same order as it is written. And the main uh, key point of session consistency is, let's say there are two databases as per our diagram that we have here. One is in US and another one is in India. So let's say the whole of US is in a single session. By like we are assuming that the session is getting shared between all the users which is using the database in US, and the same goes for India. By assuming that, let's say a user has updated something in the US database, and when in India I try to read that data, which knew the data, if the sync has not yet happened yet, I will get the stale data, which is same as that we saw in eventual consistency. But let's say I have updated it in US. I live in US and I have updated it there. And I only try to, I or any other person who is in US tries to read the data from US server, they will get the updated data. They will get the latest version of the data that is in the US database. So there is a difference in consistency, but the user who tries to fetch the data in and resides in the same Azure location gets the latest data. So that is a key difference. And how we get the ordering of the data, when it gets synced, the data is ordered in the same way as it was written. Like let's say it was A first and it was then A, B, and C. It will get synced in the same similar way. And the next consistency we have is consistent prefix. So what it tries to achieve is only to get the sequence in order and nothing more or nothing less. Like we want to have the sequence in order at least. It will not, it doesn't guarantee that we will get consistent data, that the read will be always be the latest one, but we can be rest assured that the data that we are getting is in order, and we don't have a mix up of writes. Like let's say the value was A and then it's set to B and C. We will be not reading C before we have read B. So in consistent prefix option, updates that are returned contain some prefix of all the updates with no gaps. Consistent prefix consistency level guarantees that reads never see out of order writes. It provides write latencies, availability, and read throughput comparable to that of eventual consistency. It is same as eventual consistency, but the order is maintained. It guarantees order that suit the needs of scenario where order is important. Moving on. Uh, this one is our last consistency, which is eventual. Here, there is chaos to see. Like in US, I will write something, and when we read, and in India, when we read, they will not match because let's say the sync has not happened yet, and the data is different in both the databases. In eventual consistency, there is no ordering guarantee for reads, and we also don't have any ordering guarantee. Let's say I have read the data, it was A, but the data is already changed to B. So when when B will be arriving, then I can say that the ordering is not valid. Like I have read A before I have read B. because I have queried it before it was synced, of course. In the absence of any further writes, the replicas eventually converge. Eventual consistency is the weakest form of consistency because a client may read the values that are older than the ones it had read before. Eventual consistency is ideal where the application does not require any ordering guarantees. So this was the consistency that we get in Azure Cosmos DB, and we can choose from all these options that are presented to us while creating a container to store our items. Like we have to design our database, like how we want, like do we want more throughput or do we have to maintain, absolutely have to maintain the strict consistency of strong, like strict consistency. Like if we have some critical data like bank details or something like that, then we have to like uh, maintain strong consistency. But if we have like some data, like some application where the ordering is not important and we can have inconsistent data or the reads, or the application can uh, present to its users inconsistent data, then it's like okay, like there can be lag in gaming or something, like gaming data can be inconsistent sometimes where there it takes some time to sync with other databases to load. So it is like given that it will take some time. So there we can use eventual consistency, and we can also be smart and use anything in between. If we scope out the problem or the solution that we are trying to build and see that if any one of them can be a better candidate apart from those extreme ends in the spectrum. Then comes the main part, which is discovering request units. So request unit is a token of token inside Azure Cosmos DB. So by token, we mean that this is how Azure measures how much resource has to be allocated. Like in a database, we have CPU, memory, and the RAM, all other uh, hardware requirements. But in Azure, what they have done is they have consolidated all those different hardware requirements and made their own unit, which they call request unit. And this is how we get built. So it is very important to understand what these are. So we have to pay for the throughput we provision and the storage we consume on an hourly basis. So by hourly basis, how much throughput and storage we are consuming in an hour, then we calculate it for a month, and then we can estimate it how we'll be needing it in a year, in a week or a month. So basically all database operation is normalized by Azure Cosmos DB and is expressed by request unit. So RU for short. So cost to do a point rate, which is just reading a data which is in there, which is fetching a single item by its ID, and partition key value for 1 KB item is 1 RU. We have 1 RUs per second, like it will read 1 KB data per second. So that is also a speed that we can expect if we have 1 RU allocated to our container. We also have three modes to choose from when we create a container per se. Like we have provision throughput mode where we set a bound to what uh, what throughput we expect our data to be read from. We have a serverless mode where we get infinite throughput and it gets scaled as the user requirement gets increased. And this is also the costliest, I believe, that there is no upper bound to what can be given. for our data. And also we have a auto scale mode. So first, let's say we have 400 RUs, 4000 RUs provisioned for our single container. And as the requirement increases, it gets incremented by 100 RUs or 400 RUs as we have set in our rule. We can auto scale the request units, the throughput and the storage requirements uh, in our database. Before we explore partitions, we'll be going through uh, Azure portal and making ourselves a new Azure store, Cosmos DB store, Cosmos DB account. And inside that, we'll be creating a database and like a container and a database. And let's see how that works out and all the different consistency level which we went through by this all this theory for now, like the theory that we went through, we'll be seeing that in Azure portal for ourselves. So let's move on to Azure portal now. Uh, in Azure portal homepage, if we press this page, we can search Cosmos DB from here. You can see a service is listed for Azure Cosmos DB. Here I've already created Azure Cosmos DB account. We can go ahead and create another one. If we hit create, it gives us an option to, at first option that we get is to choose the API that will be used. And to be certain that this API choice cannot be changed after we have created the account. So we have to be certain what API we have to choose. So I'll be selecting SQL data for now. And here we get the form to fill up different details. So it asks us for the subscription and then the resource group. So I have a resource group called session 3. So I'll be setting that, or we can create a new one as per our need. So I'll just be having the session 3 resource allocated inside. Like I will be giving the name session 3 resource for this Cosmos DB account. And then we want to give it a account name. My Cosmos ABC. And the location, I'll be setting it to US West. And it wants us to choose a capacity mode. We can go through and check it what it means in the documentation also. But let's for this demo, I will be going to provision throughput. And next we have geo redundancy. I've disabled it. Geo redundancy uh, is what we discussed in our last session in top storages, how it will be replicated to other geolocations as per our choosing. So we'll be keeping it off for now as we'll be replicating our database anyways to other location or other Azure data centers. So we'll be keeping keep it disabled for now, both geo redundancy and multi-region write. Multi-region write is we can also enable it, I think, in after the database is created. So that will not be a problem. So hit review and create. validation is success, and the estimated time it says is 2 minutes, and this 2 minutes is the threshold time, like for any configuration that we have to do in Azure Cosmos DB. So maximum time that it will take is 2 minutes. That is the worst case. So like let's say we want to add another resource, another database in another region, or any configuration, failsafe management, anything like that. The estimated time is 2 minutes maximum. We can go through the selections that we chose while creating our account. If everything seems all right, then we hit create. It says initialize deployment. Will take some time to deploy. So as it says deployment in progress, I can go back and we can see that it is in progress. For the time being, let's say I go to already created account that we have here, which is my Cosmos 123 till this deployment is in progress. So this one is a account which I created earlier for testing purposes. So this is the overview page for this account. And here we have Data Explorer, where we can see the resource hierarchy that we saw. Like we have this is a database. The database name is to-do list. And inside the database, we have containers called items. Inside item containers, we have different items. And we also have option to write stored procedures, triggers, and functions on this container. So this is the hierarchy. Like first is my account. Second is the database. The third is the container, and inside container we have different items. So as we can see, we have currently we don't have any items present. So if we want, we can create an item. Now we can see the resources deployed. So let's go to the resource. This is the Cosmos DB account that we just created. We go to Data Explorer, we will see that we don't have uh, any containers for us. So let's create a container first. So it will ask which database you want to put our container in. So as we don't have any database right now, we will have to create a new database for this. So we'll say new DB, and it gives a option of share throughput across containers. You can check it or doesn't check it. We cannot check it as per our news. I will keep it checked for now. Uh, Here is the throughput auto scale. It says that your database throughput will automatically scale from 400 URIs to 4,000 based on the usage. And it also says the estimated cost for this kind of a throughput. And it is estimated monthly cost for this kind of a 4,400 to 4,000 auto scale. It can, if it is in the lower range, we will get $35, and if it's like 4,000 RUs per second, we will get 350. So grows pretty fast if it has to scale. So that also we have to keep in mind. So it's better to keep it manual and set the monthly cost to a minimum that it is in our control. We will not get like very high if something happens. So we have to give a container ID, give container, and here it gives us an option to choose a partition key. I will keep it as default for now. Let's hit OK. The new database was created called new DB, and inside that we have new container. And here we don't have any items as of now, but we can upload. We can add a new item. Here ID is the default one. Uh, let's say I have I give only two data inside it, save. Before there was a syntax error, that's why we didn't have the save option disabled. So now if we hit save, it will the new item will be saved inside a new container. So these all data is backend based, so it will be auto created for reference. This is a timestamp that we get. So let's say I want to create a new item, and this item ID will have to be different. Let's say in another item I will give the same ID. It says the document creation failed because the ID is same. So each item has to have a unique ID, and also because the partition key is the ID which was default that we selected when creating this container. So let's say I give it 1, 2, 4, 2, 3. Let's say I can also give properties to it. So we can also have nested documents inside it, like class, which will be having standard. And can also have, can save it. So the document ID has to be different, and the data inside this document can be anything of any structure that we want. We don't have a specific requirement that we have to define the document structure while creating this container. That's the, like, I see the main benefit of having a NoSQL type of a database. So these are our two items that we just created. Moving back to the slides. Okay, another thing is so this was while creating. This is how we create a container inside a database account. And now going to the planet scale Cosmo DB, that is the main, uh, like the main point of having a Cosmo DB account is we can replicate the data, add or remove resource in any part of the world by a click of a button. So how we can do it? Like add another resource in a different part of the world. We have in settings replicate data globally. So it opens up like a cool map where we get all the points of all the Azure centers, Azure storage accounts. So from here we can select any account that we want to replicate our database in. So the same data will be available to another database which is in a different part of the world from where it is installed right now, which is West US. So let's say we want, so India is always experiencing high demand. So let's move on to uh, West East US. It gives us a warning that as you add a account, as you add a region to your account, it will be build like the additional RUs and storage, like it will get doubled automatically. Like this, if uh, like somewhat doubled, we will see that in the like the pricing calculator, which is built into Cosmo DB. It says that it will you be built for additional RUs, and storage will be the same, right? So any data that is copied in the any data that resides in West US database will automatically get copied in the East US database. So the storage has will be there. So even if somebody doesn't read data from this database, even then storage cost will be incurred in the bill. So that's this. It says the read region is East US because I just selected. If I doesn't select this, then the right region and read region is only single one, which is West US. So let's select East US as a second region and hit save. And here we also have an option to configure that was mentioned before while creating the account of choosing do we want multi-region rights to be enabled or disabled. So currently it is updating, configuring. While it is configured, it gets blank, but you can move on to the consistency part, which we discussed in great length for each of the one. So we have 5 consistency and they have made a nice animation so it doesn't get confusing for each of the consistency levels. So by default, it is set to session because it is the most widely used consistency level both for single region or globally. So default by default, that is set to the middle ground, not to left or to right. So we can check the animations if we forget what this means by heart. So as we can see, the in session consistency, the ordering is same, and also let's say if I zoom in a little bit. Okay, so in West US, some data is there, and the same data gets replicated in the West US database. No, there is a there are same sessions, session A, which is in West US, and East US, and the data is similarly read, all the three of them. But as the session is different in North Central US, the data is in same order, but the consistency is not followed. So this is like shown in a nice manner with a animation. Same goes for prefix consistency. As we can see, the red tune comes first, and the order is maintained even though the consistency is not maintained. And for strong consistency, all the data is same and synced for each of the regions. For bounded staleness, let's not go into the days and hours for lag time. And inconsistency prefix and eventual there will be a mix-up as expected. So that was some demo, and our resource got deployed, configured. Start. Let's go back to replicate data globally. Now we can see that we have a write region which is West US and a read region which is East US. So whenever data will be written, it will be written in the West US. And if a user is like if the user is near the East US region, they will be automatically uh, like transferred to be read data from East US region. And if they are in the if they are near West US region, they will be redirected to read it from here. So that is done uh, like that is implemented in Azure only, Azure Cosmos DB. We don't have to do anything for that. The sync and the redirection of the requests are handled by Cosmos DB. What I want to show is for that we have to let's see. Now if I enable the right multi-region right, it will say that both regions are selected for read and write. Just is selected, and if we add another database, let's say East Asia, I just want to show the priorities that we have. Like if I add more than one read region, then we will be having uh, automatic fail. Like let's discard it. We have two options of failovers. Like let's say the right database fails for some reason, then it will automatically switch to the read region that we chose for our write purposes. So it says it. Do we want to enable automatic failover? If we select yes, then we have write region that is US and only one read region which is East US. it says that it means that when this write region will go offline and any user wants to write data, then this database will be used for writing also. Like it will be the primary database will be switched. So currently we can see that the priority is one for it. But let's say we add another region, which is East Asia. Say take another some minutes. It's taking time because all the configuration and the data is getting synced across the globe, like literally across the globe. So it is taking some time. Even though we don't have much data right now in this count. And this is account the scope to the account. So this any all the database that we have inside this account will be replicated, as this is scope to my Azure Cosmos DB account, and not any particular database or a container will be replicated. The whole account data will get replicated. So that's something that we have to keep in mind. While it is loading, let's check the pricing calculator. We can go to the pricing calculator and have a rough estimate of the prices that will get charged for the resources, get a rough estimate of how uh, things are. So let's go set it up. Uh, Inside the database, so the settings, it's the scale, I guess. So this is a nice pricing calculator that we have. So if we have a SQL single core, the number of region is just one. Multi-region write is disabled, and workload per region is less of everything. An item size, let's say 10 KB, 4 KB, let's say. So settings are on that. We have to recalculate whenever we change something in this. Total data stored in transaction store. We have set it to 10 GB, and each item in the transaction store will be like roughly item size, expected items or document size will be 24 KB. So let's calculate. Uh, it gives us a estimate of 29 US dollars for a month. For and this is the API. So we have Cosmos DB, MongoDB, and uh, Cassandra. So SQL is selected for now. So this is the speed that we are expecting. So point read is 50, create 10, update per second is 10. So one query per second is 1 RU. So it is currently at 1 RU per second. 1 RU per, yeah, 1 RU by S. So let's move it to 100. just doubles or triples. 284. Like now it is 100 RUs per second, which we have worked given it to workload. So let's say now the number of region is just one. So and the cost is 87. So if we just move it to a single region more, then you can see the cost just doubles. So as expected, all the resources will be uh, copied to another region. Even if we don't use it, if we increase the number of region, it will like drastically affect the pricing model of our solution. So while we have all the required specifications in our hand, we have to choose carefully of how we want to like designing and what we want and how we want to uh, have the pricing model to what the resources that we, because in here we have unlimited resources and we can replicate it to unlimited regions, like many regions. How important is our data as person? So these are okay. So now we have two read regions, which is East US and East Asia. So if we now go to automatic failover, two regions. Now we have three like regions, and we enable it. We have priorities one and two. So we can move East Asia up a notch. So if the right region fails, East Asia will be the first choice. And then if East Asia fails, East US will be the second choice. Like if it is also not available. So that was how we can set this okay, updating. So now we can see the selected regions gets darker. Will take some time to update. So that was the priority that we can set for if in case of any failover, any blackouts or anything in a single data center. Moving back to our slides, now we'll be covering the partitions that we get. So what are partitions? So a container is divided into distinct subsets or logical partitions. Logical partition, as the name suggests, is nothing but how we as a end user or the administrator of Azure container will be viewing our data resource to be divided into like let's say, and it will be divided as per the logical partition that we choose. So before logical partition, we have to understand what the partition key is and what the key value is. Logical partitions are formed based on the value of the partition key that is associated with each item in a container. All the items in a logical partition have the same partition value. Uh, so the next slide. So what partition key and what partition key value means is this is a let's say uh, an ID. Like, let's say ID is a partition key path. We have a document with two items like two values. One is the ID and one is name. So if we select ID as a partition key, what ID is the like the value. It is called partition key path, and the value for this path is 0, 1. So here the ID is key path and 0, 1 is key value. So this is how it is named in Azure. In back. So what it says is, let's say a partition key is chosen from a container, like all the items that are present in a container. So every unique, when the item ID is unique, then then the container will be partitioned into that many partitions will be made. So let's say I have ID is chosen as, let's go back to our container that we made just now. Here as the here as I this ID key is to like selected as partition key. Whenever there will be a unique ID for us, it will be for every item. This container will be divided into that many partitions. Let's say now we have two unique IDs. So we have two logical partitions for this container. We can say like that. We could have also chosen something like category, like some value other than the ID, but we chose to we selected the default one as ID. What we can do is like let's say uh, like in a college we have different streams for students. So that stream can be uh, ID, like partition ID. Like we can choose computer science or electrical engineering or mechanical engineering. So the container will be divided as there are two or three branches as per the branches, and the resources, while somebody tries to query something, it will get divided among all the different branches. And then comes the concept of physical partitions. Physical partitions is actual implementation of partitions uh, like the CPU resource and memory as done in the backend. And the good thing about it is that we don't have to care how it is done. It is absolutely taken care of by Azure for us. So what we have to do is just get the logical partition right. So as per our needs, how do we want to distribute the resource into different partitions in our container? We have to get that right, and Azure will Cosmos DB will take care of how it is implemented in physical form in the servers. Another thing to note is that one or more logical partitions are mapped to a single physical partition. So a single physical partition in CPU structure can have one or more logical partitions. So we don't have to care about that. So what we can be rest assured is that one logical partition can have to be mapped in a single physical partition. It cannot be divided. A logical partition cannot be subdivided in itself. Like it has to be mapped to a single physical partition. So that we can be rest assured. Like if we logically divide a uh, container by its throughput, like if we assess that this partition will be having 200 or 400 throughput, we can be rest assured that it gets that or more than that, but it cannot get less than that. So next is physical partitions are an internal implementation, as we discussed, of the system, and they are entirely managed by Azure Cosmos DB. We don't have to in distributed system. It is a real pain to uh, configure different partitions across different deployment centers regions. So as it is automatically picked up as per the key item IDs, like partition keys by Cosmos DB. It makes developers and the administrators life very much easier, and they can focus on the configuration of data and how it relates to their application. Next is throughput provision for container is divided evenly among physical partition. So as we created a partition, we saw that we have to give a threshold throughput or a unlimited seamless like serverless throughput. So when we create partitions, that throughput will be divided evenly. So if we have three uh, partitions, it will be by three for the total throughput that we assigned for that container. And a partition key design that doesn't distribute requests evenly might result in too many requests directed to a small subset of partition that become hot. So if we don't if we don't logically divide partition in a right way, and we get too many requests for a single partition, like we have to see how the request will be handled, like how the requests will be made for our data. So if we partition in such a way that all the uh, data that is ever will be needed is in a single partition, and another data that will be never needed is in a different partition, then of course we'll be getting all the requests in that partition only, and we will be wasting our throughput that will be divided in the another partition. So that is what it means by becoming hot. So that is not efficient utilization of resource as in our scenario. Yeah, so stressing on the topic of choosing partition key. So selecting your partition key is a simple but important design choice, as we saw in the scene of our hot partition. So, and another thing to keep in mind is once you select a partition key, it is not possible to change it in place. So what changing it in place is, we can't change the uh, key to something else. So once a container is created, the partition key is set, it is set for uh, the time. We have to like copy the contents to another container with a different partition key for it to change. So that container partition key will not ever be changed. We have to delete it. And another thing is that when we uh, delete the resources of items of a container, it automatically deletes the partitions also, physicals and logical. But the container is still there. So as we put new items, it will all then again make the partition for us. Another thing to keep in mind while choosing the partition is some simple like two scenarios, like to choose, is our containers read heavy, large read heavy containers, or small read heavy containers. So if it is large, then partition key that appears frequently as a filter in your queries will efficiently route queries to relevant physical partition. So what it means that if we have partitions like keys with different names, like uh, let's say we have different students, taking examples of students again. So we have different students, if we have hundreds and thousands of students in India who take computer science as a stream, like lakhs of students, and same goes for other branches. So if we logically partition our container according to the streams, uh, then we can be rest assured that the physical partitions will also be done by the streams. And when we query the data, we can apply the equality filter. By equality filter, we mean the equal to, like select students, star students from this database where student stream equals to any stream, like uh, computer science or mechanical engineering. So when we use the equality operator, we are making a efficient query choice. Like we are we are setting the query to be routed to that physical partition only. We can be assured for that, and it makes the query better or more efficient. And same goes for if it is small. As in our case, we have a small item just with only two items. That's like if we have a small read heavy containers, then item ID, which is the default key for our document in any item, that can be a great choice for a partition key, as there will be like many partitions, physical partitions that we met, like many, it means like number of items that are in a container, that many physical containers will be created, and we can efficiently distribute the resources among different physical containers, like reading and writing, like it will be distributed among every item. So it can, every item will be having the same like balanced RE. So these are the some key like fundamental insights, or I would say things to keep in mind. There are many others while choosing the partition key for our Azure container. Uh, let's go to our portal. Okay, so we can create a new container, and you can see with the ID we can select it to stream and get the database or create the container, and the stream will be the unique keys. Every sorry, yeah, the stream will be set as partition key. So wherever there is a unique stream key, then another partition will be created, and that will be set while creating the container. That was all for the partitions. So moving on to the last segment is a simple web .NET application, which we will be using to create a resource, create a database inside a storage account, and then creating a container and inserting items in the container, getting those items back, updating it, and deleting it. So basically, the CURD functionality for that is required or expected in uh, any database. Connect that with an application. So going forward, we set up this project in Visual Studio, and only requirement that we need is this NuGet tool, which is this one. Azure, Microsoft.Azure Cosmos. This is the version 3 Microsoft SDK, .NET SDK, which uses, which we'll be using to query the Cosmos DB account. So I have set it to the debugger is set to this, and we'll be stepping it one by one. So to connect it to our storage account, sorry, our Cosmos DB account, database account. First, we have to, how it will know that which database account to be connected to. So for that, in app config, we have endpoint URI and primary key. And this we have to set. This is already set to some other account, which I'll be deleting. And we'll be setting it to the account that we created just now for this session. And where we'll be getting that key? We'll be going to the portal. And there are inside settings, we have keys. this is our storage Azure Cosmos DB account that we created just now. And inside that, we first need to copy the URI and paste it to this is the endpoint URI. It starts with the name of the storage account, like Cosmos DB account. This will be our primary key. These are read-write key. We also have read-only keys that can be given to other applications to just read the data. Save it and start our application. Before starting our application, let's go to the Data Explorer. Have a look at what we have. We just have a single database, which is called new DB for now. So when we start it, we create a Cosmos client with the endpoint URI and the primary key. It is getting fetched from our app.config. So we are getting this return. And now we move to the function which is create database async. So this will be creating the database for us. And it does by calling this database. If not exists, then we create it. We give it a database ID, which is set in here, which is family database, and a container ID is a family container, which we'll be creating in the next method. So as we step over this function and it gets executed, the output that database created, which is called family database. If we go here and refresh, we can see this. Okay, I think it created in this. Um, Sorry for that. So moving on with our presentation. Okay. Now let's say we create the container. The container is created. Yeah. So it is creating in with my previous account that I created for test purposes. We'll be doing it in that only for now. So create container calls create container if not exists. So if the container ID is unique, then we create a container inside this database. This database is we are getting it the response object from after creating the database. and inside that this database we are creating the container, and it says container is created. The next function that we have is add items to the container. We are having a data class for our family. We have declared a family data class, which is C sharp class for modeling our data that we have. We have nested data for parent, child, and pet address for a single family. So a family can have many for parent array, a child, many children, many parents, and address, and each child can have pets and so on. We have modeled it according to C sharp classes, object models as we say, and then we are setting it manually here, giving it some default values, and then inside the catch, like if the container, like we are trying to read items or with the ID, as it is not yet created, we will get an error and move to the catch. So in catch, we are creating create item missing, we are calling, and creating setting this Anderson family object which we created here, and creating a partition key which is new partition key Anderson and last name. And this is the partition key for this container as we set in here this method. Like when we create a container, it says that so the second argument is the partition key. So last name is the partition key which we are providing as a partition key. And then we declare the Wakefield family. We set the data for Wakefield family. Again, we call create item missing and insert the Wakefield family into our container family container. It says created item twice because first the Anderson family was inserted, then the Wakefield family was inserted. The ID for Anderson family is Anderson.1 and same this one for Wakefield. So we can go ahead and check it in our database. Now it has two items. Uh, According to the object that we declared in C# code, we have the same structure, but because family name was not set, we have the data as null, and same we have address for the Wakefield family. Yeah, so these are the two documents that got pushed to to our container. Now querying comes. Like in query, we use the SQL API that is exposed in Cosmos DB as we created our account in SQL using like selecting SQL API. So we can use SQL statements to query it. Like we can use select statements inside and get the data that we want. So here it this is just simple query to select the last name is Anderson, and we get all the data where the last name is Anderson, and we loop through it and print the family name. So it just gives a single item, and now we after querying, after reading it, we updated the family name, which is replace family item missing. We are reading it first, then reading it by like where the while calling read item missing, we are passing the item ID, which is the unique ID for that item inside that container, and also passing the partition key as we mentioned. So if we pass the partition key, it will make our query like a lot faster, and it will route it to that physical partition that is made based on the logical partitions in our end. So we are reading that data and parsing it to item body. We are then updating that item by values that we want, and then calling replace item async on to update it in our database. So IDs are updated, and then we delete the resource, and then delete the item where uh, delete the item where family ID is Wakefield. So we are deleting the Wakefield family item, and then we are deleting the whole database and the container inside it. As we can see, if we come here and refresh now, the whole family database would be gone. So it is not present here now. So this is how we can use CERT operations to create or like, use CERT operations inside our Cosmos DB via .NET Azure.NET SDK. So that's all for this session. Thank you for joining. Any questions? I will be glad to answer them. Any questions?
No, I guess thanks, Rishav. Thanks for this.
Thank you, sir. Everybody have a nice day. Thank you for joining. Okay. Bye.